what the malware family is, and therefore what they would need to do about it, or what whether it's something new. Like a researcher is usually looking for something new and interesting, and then the incident responder is trying to just find something that's similar so they can get a shortcut to identifying what malware family it is. So also, I wanted to pause here and talk about the nomenclature problem. So this is a huge debate among the malware analysis, reverse engineering, and the DFIR community. And so there have been attempts at making a unified language to talk about malware. I'm not going to actually go into details about some of them because they're fairly complex, but one of the things that I have thought about myself, and this is just my own idea and my own opinion on the problem, is I think that there is a way to solve the marketing problem and the nomenclature problem and actually still satisfy a marketing department's need to be famous, because that's what the driving factor there is, to be famous in their environment. And so this same problem was already solved in biology. So my background is actually in biology. And so the Latin name for organisms does have a factor in there for the fame of the scientists. Like if you look at the Latin names of many organisms, they'll have either the scientist's name or something funny that the scientists wanted to put in there. There's all sorts of fun factor in there, but it's still a uniform nomenclature for organisms. So in a way, I think the sociological problem that we have that's part of the marketing problem has already been solved. It's just we need to agree on a single nomenclature and then kind of allow it to grow from there. So I've digressed a little bit. And so the second thing that you want to do is, once you've identified the malware family, then what I want to do is take a large body of samples, something like the body of samples that might be at VirusTotal, for example, or the body of samples that are reversing labs, which I think if you were here for the talk earlier, he talked about that as well. So there's large corpuses of data, and so within a set of samples, I want to find other samples that are related in some way to the sample that I'm looking at right now. So that's a way to find other samples, and then from there you can jump from those other samples to perhaps you'll look at the hash values, and you'll find that those hash values show up in an intelligence report or some company's blog post about a particular piece of malware, so they can use that information as well. So I want to begin talking about identification. The first identification method I want to talk about, and this is sort of the worst identification method. So it's the one that you will get the least value from, but is also probably the most accessible. It's the easiest to get the data for. It's nearly always freely available. You can look up on VirusTotal or other websites. You can see the scanner results. And if you're not working on a piece of malware which is sensitive, you can always upload it to one of these sites and then get the scanner results back. So I'm going to walk through my methodology for interpreting AV scanner results, and also I'm working on some code to turn this into an algorithm, and so it should be on GitHub fairly soon. And if you want to, if you have any ideas or any problems that you see in my method here, please let me know. I'd love to collaborate on this. So one of the main problems that you'll notice is many of the AV scanner companies, they share a scanner engine. And so instead of actually rewriting their own scanner engine, they white label or license another company's scanner engine and then call it their own and then sell it. And so when you get a body of AV scanner results, this actually causes a little bit of a mathematical problem for you, because it looks like you're getting the same results from lots of scanners, but actually you're only getting you're getting one result, and you need to discount or at least count these as one scanner, right? So you'll see the scanner result, and this is one I just picked because it had this sort of random looking number at the end, which was, from looking across the other scanners, this number is very unique. And so this scanner result came back from Adware, Alyac, Bitdefender, Emisoft, F-Secure, GData, and MicroRolled eScan. So these companies, at least at this point in time, were sharing had a shared engine or components of the engine and had the same results.
So that's when you do the scan locally on the system.
Sorry?
This is, you did the scan locally on the system. You didn't throw it up the virus total.
Actually, these results are from scanners that I have a scanner, a multi-AV scanner project, so these are actually scanner results of my own. But you can actually, that's the hash of the sample, so if you've got access to, well, I mean, you don't need access to VirusTotal to see the scanner results there. So you'll be able to verify these results. So one of the things that you encounter with another thing that you see with AV scanner results, and there's basically two diametrically opposed forces at work in AV companies, and they're actually driven by the bottom line. So it's this is actually a money problem. It's not necessarily a conscious problem that people have said, all right, I don't want to do this, I want to do this. No, it's more a money thing. So as you can see, you've got the generic beer, and then you have DC Brow, and actually, yes, this is an advertisement for DC Brow, great company, my friends Brandon and Jeff, go check them out. So you get a specific detection as opposed to a generic detection, and so when you have a generic detection, you're basically covering as much malware as you possibly can with one generic signature. And so when you do that, the number of people and the number of resources that it takes to develop a signature that's generic, that covers lots of malware, is cheaper than developing a specific detection that goes down to a malware family or a specific actor group or something like this. So you've got very, very specific scanner results, then you've got generic scanner results. And it's cheaper to come up with generic scanner results, and so you've got a force pulling, in that direction. There are a few AV companies, and I'm going to call out a few of them, and they're, your results will vary. There are generic scanner results in there as well, but for the most part, Microsoft is probably the best. So if you put malware into Microsoft, they're going to give you some very specific scanner result. And it's also the name of the malware that they come up with. They have, a lot of times they have their own nomenclature as well. So you'd have to kind of know what this particular malware, what the name that they come up with actually means to the rest of the world. But they're very accurate and very specific with their AV scanner results. ESET, Sophos, Kaspersky, and if you have any other suggestions, please let me know, like if you've seen good results from one or another. And I've also put on here, most of these have threat encyclopedias, and your mileage will also vary on the encyclopedias as to how good the information, or how in-depth the information is there. But here's the process that I use for boiling down AV scanner results. So if you want to follow along on your own, this is the MD5 of the sample that I'm using for this. And so what I've actually done is I removed a lot of the scanner results that were generic. So anything that was generic, and actually, yeah, so anything that's generic. Also, there's a few like Zeus, Zbot, Zeusi. These are not actually specific results. These are also generics. It's definitely, like if you see Zeus or Zbot, it's probably not Zeus. Not these days, at least, unless you're in a time machine. All of these are non-generic. So these are specific in some way or another. And so what you want to do is kind of look for some of the patterns that I had noted earlier. So if you note these, so remember that set of AV scanners that all have the same result? And I'm at that little, the B down there, I'm just going to call that the same. Let's kind of ignore that one. Don't know what that means, but that's definitely, they're sharing the scanner engine, but they might be just adding their own little fairy dust. But let's call those all the same, because that's basically one scanner engine. So we've got another one. So this pair down here also appears to be sharing a scanner engine. So Avast AVG. Again, you want to count that as one. So then, and by the way, this is by no means, if you're a mathematician, like this is very like, finger in the wind kind of stuff here. Okay, so basically, since I've boiled down the add-aware to one, now I've got a word that repeats itself somewhere in those results. So it's SIMI. So SIMI is actually a malware family. And then ISBAR, also you find ISBAR in these three, and so ISBAR is another malware family. And so these are kind of the same. So, I'm going to lean towards this being ISBAR, but not really. I mean, this is totally, not very scientific, a little bit approximate, but at least I've got, at the end of this process, at least I've boiled it down to two words that I can then go and look for research that's been done on these malware families, and then I can say, like, all right, from research that they know is from these malware families, is the thing that I'm looking at actually related to these? So I could do things like dynamic analysis, static analysis, look at other features of the malware to see through a different pathway of association, are they associated to these malware families? And then once I say, all right, maybe this is part of one of these malware families, now I've kind of maybe taken a shortcut just by boiling down AV scanner results. But of course, your mileage will vary. And then, so there's another identification method, and this is one that came out, so this actually debuted last December, I think, or shortly before last December, but at BotConf in France, the folks that run Mouthpedia had a talk. I was actually there. I think I spoke after them or before them, but they debuted Mouthpedia, which is actually a lot of the data is open to the public, but it's also a closed trust-based system. So if you are a malware researcher and someone else can vouch for you being a malware researcher, you can join the community so that you can add signatures and help with detections in there. So Mouthpedia, the goal is to provide like a single resource for rapid identification of malware. And so it's basically an encyclopedia where there's a few different data points that are there. There's a potentially, so there's a huge number of malware families in there, but the coverage as to signatures and the coverage as to samples varies depending on which one you're talking about. So they do need more people working on the project to donate time and effort in fleshing out the whole corpus. But it basically provides a couple different things. So it provides a YAR rule potentially, or multiple YAR rules, and then it also provides samples of the malware, and then it provides potentially background information on what the malware family is and where it's been seen and other information like this. And also can point to different reports that are about that particular malware family. I did have to kind of go backwards a little bit because the set of YAR rules that are in there do need some help. There isn't coverage for many of the families that are in there. So to get a slide to show you all, I actually had to go backwards. I had to grab a sample that I know is one of the families and then plug it in there and then get the matched results. But again, like it's a very good place to start. It's the project is I think about only 1 year old. So I encourage you all to join the project, work on it, help out if you can. And then another identification method, my former employer, ThreatConnect. So there's a free account at ThreatConnect. I still recommend that you use the free data. A lot of the stuff that's in there was built by my team, and they're still maintaining it. But one of the things I wanted to point out, so what we did was we actually pulled in, so this is blog posts and a knowledge base article on how to use this. So once you have the free account, there is a repository in ThreatConnect of all the technical blogs and reports. So any company that publishes a blog that has indicators in it and is on an RSS or an Atom feed, all of those are pulled in, and the indicators are pulled out so that you can read the blog, and then you can actually have indicators that are associated with the blog. URL indicators, IP address indicators, host name indicators, et cetera, et cetera. So that's all there. And one of the things you can do is if you have a particular piece of malware that calls back to a domain name, you can then look for other pieces of malware that call back to that same domain name. So if you've got a particular domain name, you could try putting in that domain name or IP address, and then you can see are there reports out there about malware families that call back to that same particular piece of infrastructure. And then also, I like to say there's the XKCD, the appropriate XKCD. So when all else fails, and also not only when all else fails, Google it anyway. Like whenever you're doing, just Google whatever you've got, because you've got the how to become an IT expert. The expertise is Google the name of the program plus a few words related to what you want to do, and then follow the instructions. So very much related to this, if you are researching some particular piece of malware, and you've got the imp hash or the hash, SHA-286 or whatever, throw all of that into Google and just see if it comes back as being in, occasionally you'll find malware sandbox results from hybrid analysis and other public sandboxes and all sorts of interesting things that are out there indexed on Google. So always use it. And so that's the end of like the kind of basics. Now we're going to get into the more sort of esoteric malware analysis techniques that can be used for association methods. So static analysis, if anyone is familiar with malware analysis, there's two basic categories of analysis. So there's static analysis and dynamic analysis. So static analysis is where you're basically looking at features of the malware file without actually running the malware file. So you're basically analyzing maybe the source code, not the source code, but the assembly code. You might be analyzing some of the features of a document, the author of the document, any other like the modified dates and all sorts of information. There's a lot of metadata in a file that you can access without running that particular file. So this is all called static analysis. So one of the a couple of interesting hashes are SSDeep. So SSDeep is a context-triggered piecewise hash, and if you think about it, basically, if you have an MD5 hash or a cryptographic hash like that, and you change even a small piece of a file, like change 1 bit, flip 1 bit, or something like that, you're going to change the entire hash value. And that's what it's designed to do. It's designed to detect small changes like that. But what SSDeep does is it kind of, if you think about it, you break a file into pieces, and then you look at the hashes of the pieces. And so therefore you can take a whole set of different files, each of them broken down into pieces, each of them with like little hashes. And so when you compare those, you'll be able to see if this file, for instance, is the same up until here, only that part of the SSD hash will change. And so essentially what you've got is you have a file. So if you think about all of the samples that you have in your library as points in a three-dimensional space, you've got one point which is not only it's basically the file itself. So the file itself is always going to match itself. So that's the point in the center. And then you've got other files that are a certain distance away from the file that you are looking at. And so what you want to do is say, you basically have a sphere of what your tolerance for how similar something might be. And so if you decide everything that's a certain distance or less away from that point, which is the file, you're going to say is related to that file. So that sphere and everything within it are all a cluster of files that are matched, to that SSD that you're looking for. And so it's actually a fairly powerful method for comparing files, but the huge problem is almost all malware comes in a packed form. And so a packer, what a packer does is takes the executable that gets loaded into memory and run. It actually takes that data and either compresses it or encrypts it or does something to it to obfuscate or encrypt it, and then put those in another executable file. So there's a part of an executable file which has the payload that you're looking for inside of it. And so the problem with SSD and many of the corpus of malware files, they're all packed. And so what you're doing is you're finding the SSD similarity of the packer. You're not finding the SSD similarity of the payload that is delivered and run. So that's one of the failings of SSD. But if you've got a system where you've got all of the unpacked malware and you're running SSD on unpacked malware, you can have better results. Import hash. So imp hash is also a very, very powerful tool for comparing malware files. And in PE, so PE is the standard for executables in the Windows world. And so you have an import table, which is the functions that are imported by that particular program. And so the import table, if you take the import table itself and make a hash of that import table, you can then find other PE files that have an identical import table. So if you have an identical import table, chances are that other file, might just be randomly the same import table, but probably not. They could be related to each other. So this just gives you a way of kind of dipping into a pool of files and pulling back some that are potentially related to the one that you're looking at. And then you need to dig deeper to verify, are these actually related, or is this something that is just, happens to have the same imp hash? But there's also, like I said, one of the problems with SSD, of course, import hash also has its own kind of problem. So if you're looking at malware which is written in .NET, all of the import hashes are going to be exactly the same. So when you find a piece of .NET malware, and you take its import hash and you plug it into VirusTotal, for example, you will have just all of the other .NET files out there that have that same import hash. So you're not going to, you won't be able to find anything related using import hash if you're in the land of .NET. So file names are actually very interesting, and they're not necessarily interesting on their own, but they're interesting when there's a pattern that's used to create the file names. So has anyone heard of like a domain generation algorithm, DGA, domain name? So a DGA is basically an algorithm that someone writes where what it does is it generates a domain name, a new one, and that domain name is generated based on a particular algorithm, right? So it will, maybe it's a cryptographic algorithm, maybe it's some algorithm. So you're going to get a pattern in the domain names that are created. So if you think about that from the algorithm perspective, a similar type of algorithm could be used to generate file names. So you have like a file name generation algorithm, or it just repeats a certain set of file names it uses. But basically, if you can develop a regex based on the algorithm or the possibilities of the file names, then the file name does begin to be a powerful way, or at least one additional method of relating two samples together. So if you've got two samples that use the same algorithm to generate file names, that's one indicator that these two things might be related. And also, you're going to see a couple of things here where I lean on regex and developing regex patterns to match with what the adversary and what the malware is actually doing. And this is another example of that. So, and I included this. So I know that my talk is about comparing malware files, and this doesn't get you anywhere about comparing malware files. I threw it in here just because it's related to the next slide. And so when you've got a malware payload, often that malware payload will sit on a compromised website, and then the malware that's on your machine will reach out to that URL or reach out to that FTP site or whatever and download that payload and then run it. And so the URL structure of that download URL can't be really used to relate malware families, but what it is related to is the vulnerability in the CMS that was used, to exploit that website and then use it to host your own or someone's malicious files. And what I'm talking about here is, for example, if you've seen some of the WordPress themes like 2016, if you see any of these, they're all vulnerable and they all have massive problems. You'll see those in phishing URLs, and you'll see them in malware hosting URLs all the time. And I know, by the way, anyone here who's a fan of regex, I understand this is a very, very, very simple regex. There's no magic here at all. But it's actually more just to demonstrate for people who are not familiar with regex, how this might actually work. And this is not a very powerful regex. This is more just for demonstration purposes. In a moment, a couple slides, I'll show you an actually powerful regex for identification of APT malware. And that leads me to this next topic. So the C2, so this is actually the command and control infrastructure where the malware is calling back to get commands to deliver data that it's stolen from the victim. And so the structure of the C2 URL is directly related to the malware family. So this is something that was set up by the malware author or by the malware itself, or indirectly by the malware author. So this is an example of a regex for identifying a particular APT group's malware family. And so this is one of the things that happened earlier this year. So this is from January, February of this year. And so this particular adversary had to change their tactics because most of their targets were on either Google for Business, Google or Gmail email infrastructure. And so they were having a big problem because Google had started getting very good at finding their attacks and blocking them before it even gets to your spam folder. And so the adversary needed to change their tactics, and so what they did was they put the first stage of their attack on Blogspot. And so what this did was it circumvented Google's own malware protections and detection, because Blogspot is their own property. And so sending a URL inside of Gmail that's referring to a Blogspot URL circumvents all of their protections. And so This was one that was sent out to a number of different journalists, and I think you can figure out who this one might be. And for any of you that are very carefully looking at this regex, you'll notice, so there's a UID here, and you'll notice I didn't include the UID here, and that's for a very specific reason. The target's email address was UU encoded, sorry, base64 encoded in that particular query string. And so I didn't want to put one of the victims' email addresses up on my slide deck. And if you want to read a bit about this particular, this is a blog post that I wrote back in, I think, January or February, and you know, it's a bit of a jab at them because it was like a one-line forwarder as their blog post, which is a terrible blog post. They should really learn how to blog better. And then you've got EXIF metadata. So if anyone is familiar with EXIF, so EXIF is, you know, I don't come from the photography world, so I might not get this exactly right, but I think EXIF came from photography, and it's a way of storing metadata about you know, photographs. And so so it's actually grown way past photography or anything like that. And so there's a program called EXIF tool, amazingly still written in Perl, but you know, to each their own. It's a very effective tool, and it doesn't just work with photographs anymore. It works with any file you can possibly think of, and it does a lot of very cool things. And it basically does a lot of the static analysis for you. And so one of the things you can get from this, you know, actually there's a bazillion things you can get from it. Timestamps are important, like the compilation timestamp. One of the things that I use compilation timestamp for is looking at the timestamp of the file's compile time and comparing that to the time that it was submitted to VirusTotal or submitted to hybrid analysis or submitted to somewhere online. And if those two numbers are too close together, then you know that it's the adversary that's submitting it, testing their own malware. So that's an important, you know, thing to note. So, I mean, I could spend years on EXIF metadata, but I encourage you on your own, go look up EXIF tool, start messing around with it. And by the way, EXIF tool does now have a JSON output. There's a flag where you can output the data in JSON. And so it's super easy to write a Python script wrapper around that and like suck out the data in JSON and then use it as you need to. So this is another example of you know, ways of relating malware. So the code signing certificate. So code signing certificates can be abused by the adversary in many different ways. So you can actually create a fake cert, of course, and then, you know, a self-signed cert or a fake cert of some type. Or if you're really bold, you can go steal someone's actual certificate, you know, compromise some company or a developer, steal their credentials, and then start signing software as them. And then also, you can have something that looks like it almost is a signature, but there's something broken about it, like it doesn't work. But all of these methods can be used to identify related malware. So this is one of the folks on the research team at Reconnect. So they found, so this is a sample which was found to be Desaruby APT. And there's a valid signature from DTOP tools. And then if you look for this same signature, they were able to find other samples that were related to that. So and used in previous attacks. And so one of the reasons why this is important is it tied a number of samples that were unknown to a fairly famous breach that you might be familiar with. So this is the Anthem Wellpoint. So this is definitely not Wellpoint's hostname, WE11 point. But this is one of the one of the samples that was related to that particular breach. And this is another blog post that was written about that by my team, so please go check it out if you want more information on that particular attack. So there's also there's a number of other different metadata points that you can use in the static analysis end of the world. Sections, imports and exports, and resources. So this is probably a pretty busy slide, but it kind of shows this is the PE executable format, like where you find things in the PE format. And so this shows you, imports and sections. All of these are in very specific parts of the file. So they're, there's a standard, so you can go look and see that particular piece of the file. And so what you're basically doing, for example, in sections or resource, you take a hash of that section, you take a hash of that resource, and then you can, and if you've gone through and done that for all of the files that you have, you can then find files that share the same section or share the same resource. And again, just like import hash and other hashes, this is just a way of kind of dipping into the pool and then pulling back some that you think are related to the file that you're looking at, and then you need to look deeper, run those through dynamic analysis, run them through other ways of tying them together. Just because something has a shared section doesn't mean that it's related. It just has a shared section. But it is a better indication of it being related than not sharing a section. So you always need to have other methods of relating it. This is just a place to start. So this is an example of in this sample, that's the hash of the sample, and then this is the hash of this particular section. This hash. Same thing here, so RT version, this is a resource, and this is the hash of that resource. There's a couple of other related methods for finding things that are related to a file that you're looking at. VirusTotal has many different indexes that you can search through. And so one of the things that they've got indexed is called similar to. It's some proprietary black magic that they use. It's fairly effective. And also a couple, last month I went to go visit my friends at Reversing Labs in Zagreb in Croatia, and had a nice happy hour with them across the road at their local hub, and talked about malware analysis. And I actually gave this talk to them in their office, and they noted to me that they actually have their own version of that, similar to algorithm, but theirs is not black magic. They actually publish exactly what the algorithm is, how it works, and it's all right there. So, I encourage you to take a look at that. So it's just the Reversing Labs hash algorithm, RHA. But this is another way of basically clustering or finding related malware files. And then when you get into, or when you leave the land of executables and you're talking about documents, so documents have their own special sets of metadata that you can extract using static analysis. A lot of, your mileage may vary on different data points there, but some of my favorites are author. And if you're talking about, Office documents, they're going to have, they potentially would have an author if it's set. And then if you're in the land of PDF, the equivalent of the author is actually just called the PDF producer. But these two data points are basically exactly the same. They're like the name of the person or name of the company or whatever that wrote the document. Timestamps are great. Again, I talked about why timestamps are interesting. Also, timestamps are good for, if you've got a body of different files and you've got a number of them that all share the same timestamp, that's another indication they might be related. Language, your mileage will vary unless you're talking about a very unique language that is, fairly obscure. And I'm not talking about English or Russian or Chinese. They're not obscure at all. So next association method I want to talk about, so everything I've talked about so far is static analysis. And I'm not going to go too in-depth into dynamic analysis. I'm just kind of gloss over some of this stuff. But one main way of kind of finding what a malware file might be related to another one is through mutual exclusion. So for those of you that are not programmers, totally fine. What a mutual exclusion does is, if you have a processor, today processors aren't just like the 386 or 486 back in the day where there's like one processor. You now have a processor that has multiple cores. On top of multiple cores, you might have multiple processors with multiple cores. And so what you get there is a problem of concurrency. So if you've got one program, and that program wants to do something, so run some code, it needs to know that if it's running that code on a particular core, some other copy of the exact same thing isn't running somewhere else and bumping into each other, right? And so the problem of concurrency is solved by creating a mutual exclusion. So the first thread or the first program to run will create a mutual exclusion, which is meant to be kind of a unique string. And then the other one is going to look for that mutual exclusion, and if it finds that mutual exclusion, it won't bump heads with the one that is already running. And so, this is sort of the more technical version of what I just said. But essentially, what that means is that mutual exclusion, being a unique string, uniqueness is one of the inherent qualities of this, so it can be a mutual exclusion. That also means that unique string might be reused across different malware families, or across one malware family, or different samples of a malware family. So if two different files use the same mutual exclusion, they could have either a shared code base, or they could be the same malware family. Registry keys, so I'm not going to go too in-depth into registry keys, but please go read about the Windows registry. I don't want to have a lesson on Windows programming, but basically the registry, for all intents and purposes, it's a place where programs can save some data and then access that data. And so basically, there's basically a couple different functions. You can either delete a registry key, you can change a registry key, or you can write a new registry key. And so the set of changes that software makes to the registry, that set of changes can also be unique and can be used to identify shared code base or malware family. Now I'm going to kind of go advanced into some of the more fun stuff, and I forget your name, the gentleman from the talk earlier. So their company is one of the companies that does this this sort of work. And so one of the things I wanted to start with, and I know, by the way, I had the machine learning folks at Reversing Labs, and I changed the slide that's coming up. So I do know that these are not machine learning algorithms, thank you. But this is actually a talk that was given at BotConf last year. It was a workshop. I took the workshop, awesome workshop. All of the material is on GitHub. And so I encourage you to go through and work through this this workshop on your own. It's a eye-opening workshop. I'm not going to go into too deep about what it does. But basically, uses these two algorithms, and you learn how to use these two algorithms to find clusters among. And they actually used a fairly small data set just so that you can kind of have it in a classroom. So it was the zoo, which is it's a reference data set for malware. I think it's on GitHub, but don't quote me on that. Just Google the zoo malware data set. And so one of the things that I learned from this is, a lot of people think to do malware clusterization, you need a lot of GPUs and a lot of horsepower and stuff like that. But you don't necessarily need that. There are a few crafty ways of using sparse matrices and other methodologies where you're, I'm a biologist, I'm not a mathematician, so I'm going to kind of talk to you as the mere mortals that we are. And so basically a sparse matrix, from the way it was explained to me, so if you look at a matrix, there's a lot of numbers in the matrix that are all 0. And so you're basically wasting compute time by spending time having the computer think about a bunch of zeros. So there's a way to basically collapse the matrix down to only the data that is non-zero. And so that actually saves your computer a lot of processing time. And so one of these fixes everything, the other one is a roll of tape. So I also wanted, this is a bit of an aside, and it's a little bit of an advertisement for one of my friend's projects. And so this is the InfoSec Finer Things, and I encourage you to follow her on Twitter. So she had an idea a while ago to have wine pairings with malware analysis. So basically pairing finer things in life, which malware pairs best with a Malbec. So please follow this. It's more fun, not really serious, but so yeah, this is a group that I encourage you to follow. Okay, and then I'm kind of going to go really fast through this. So the diamond model of intrusion analysis, this is a way of taking different data that you have about an intrusion and making sense of it using graph theory. And this, I know I have not gone, this is not malware related, but this is actually from Star Wars. So we actually applied the diamond model to different parts of everything in Star Wars. And to be honest, the argument that happened in our office as to where things belong and how they should be related to each other was literally like a shouting match, and people were getting angry about like their opinion on where things should fit in the diamond model. And so this is a lot of fun, but it was quite a tough week for us trying to figure it out. But if you want to have the serious version of this, this is the paper itself, so please go download the paper, read it. It's a very powerful tool for finding, for making sense of an intrusion. Another association method, this is ice water, and so this is actually the link to ice water, and this is where I'm going to kind of slide this over here. Hopefully this really works. So this is a publicly accessible system. You can take a So basically what you can do is, all right, so you've got it basically clusters into one, you've got a cluster of malware that's related, and this thing has 25,514 members of the cluster. And then you can see another cluster that is two bits different, so two bit distance from this cluster. And then these are clusters that are one bit different. And so this is basically what it's comparing. So you'd see all of these are members of one particular cluster, and you can actually see visually that why they're all related. You can, even the naked eye, you can see that these are related, and you can also see where they're changing. So you can see that one little spot down here, this area kind of wiggling around as you switch through all of these. So you can kind of see where something is changing. Oh. See that?
Yeah.
Cool. All right. So that's another way of looking at what's related. Let's use slideshow. All right. And then, as you had mentioned earlier, so control flow graph analysis. And actually, I wanted to talk about a talk that this is actually quite old now. It's from 2014 DerbyCon. So this is a really good talk if you want to get introduced to control flow graph analysis, what it's used for, why it works, kind of breaking down exactly what it does. So there's a YouTube video right here. Douglas Goddard was the speaker, and actually in the video, if you open up the video, if the camera were like, maybe a couple inches this way, you'd see my head there in the front row. But basically what it does is you have a control flow graph, and if you're looking at just the control flow graph for non-library code, so if you're looking at the control flow graph of library code, you're basically developing a signature for a Microsoft programmer, and that's not something you need to do. So basically, if you remove all of the library code and all of the code that was written by Microsoft in a library or written by someone else in an imported library, and just look at the code, the control flow graph that was written by the author of the malware, you can use control flow graph analysis to find other malware that has that same control flow graph signature. There's many things that you can do with that. It is yet another way of finding potentially related files. And I always like to say, this is actually the end, I always like to say that you don't want to use one particular method. You want to use as many methods as possible. Once you have multiple ways of demonstrating something is related to another sample, the more variety of pathways that you can relate, the stronger your confidence is that those two things are related. So that's it. This is my Twitter handle. Please follow me on Twitter. And if you have any questions, I think we have 3 minutes.
Yeah, really quick, back at the start of the presentation, you were going through the commercial antivirus programs and showed that 6 or 7 of them were using the same engine. Then you had a couple other ones that were using, like 2 of them were using a similar engine. Do you find that it's the same ones all the time, or will those groups be different depending on what Trojan you feed in? Like maybe you'll get 6 for that one Trojan, but you'll feed
They're mostly clustered together. Yeah, they're mostly
you don't have to connect the dots to show
not usually
who's copying whose code. It's pretty much all the same. Okay, that's all I wanted to know.
Yes.
And I realize this would probably be a whole conversation itself, but the value of attribution of these.
Mm-hmm.
So is it just for like classification purposes to find interrelated malware?
So, I think, let me put a question in your mouth.
Okay.
Maybe.
Yeah, sure.
I think, because you use the word attribution, so yes. You're basically asking like, how valuable is this towards the goal of attribution?
Yes.
Ish. That
yes.
kind of,
Yeah.
Okay.
Something along
those lines. Okay. So as the leader of a team that does attribution often, one of the things I want to stress with attribution is attribution can never be your goal. Don't ever, that is complete nonsense. Never have attribution as your goal. Go through your malware analysis process, and attribution may or may not emerge from the process that you go through. So you're never looking at a piece of malware. Like if you're an incident responder, your goal shouldn't be, I need to attribute this malware to a malware family, or I need to attribute this to a threat actor group or an adversary. That should never be your goal. What your goal is to analyze the software, figure out what its capabilities are, figure out what it's related to, and during that process, you may chip away at something and go, that's interesting, and then attribution may emerge from that process, but it can't, it's nonsensical for that to be the goal of your process. You don't start out saying, I need to attribute this.
Well said, thank you.
Thanks. All right, thank you everybody.